Hello and welcome. In this video, we'll be diving into the fundamental concepts of relations and functions, which are cornerstones of mathematics. By the end of this lesson, you will be able to define and identify relations and functions, understand and use function notation, and determine the domain and range of various functions. Let's begin with a practical example to build our intuition. Imagine a car park at an airport. The charge you pay depends on how long you park your car. This table shows the charges. This table creates a relationship between two variables, the time parked, which we'll call t, and the charge, which we'll call c. Now, look closely at the first two rows. A question arises, how much would you be charged for exactly 1 hour? Is it $5 or $9? The table is ambiguous. To avoid this confusion, we need to be precise. We can adjust the table to use inequalities. For example, 2 to 3 hours can be written as t is greater than 2 and less than or equal to 3. This means if you park for 2 hours and 1 minute, you pay $11. But if you park for exactly 2 hours, you pay $9. This relationship can be visualized on a graph. Here, the horizontal axis represents time in hours, and the vertical axis represents the charge in dollars. Notice the use of open and closed circles. An open circle means the point is not included, while a closed circle means it is. This graph, called a step function, clearly shows the charge for any time t. This entire schedule of charges is an example of a relation. A relation is simply a set of ordered pairs that connects two variables. In our car park example, the relation is infinite because every real value of time between 0 and 24 hours has a corresponding charge. We can also have finite relations, like this set of 4 ordered pairs. For any relation, we define two important sets. The domain is the set of all possible input values, which are the x-coordinates. The range is the set of all possible output values, the y-coordinates. For our car park relation, the domain is all times t, such that t is greater than 0 and less than or equal to 24. The range is the set of all the possible charges. For the finite relation, the domain is the set of all unique x values, which are -2, 1, and 4. The range is the set of all unique y values, which are 3, 5, and 6. Now let's formalize our understanding of relations and introduce the Cartesian plane. A relation is any set of points that connects two variables. Often, these points are expressed in the form of an equation connecting x and y. We graph these relations on the Cartesian plane, which is formed by two perpendicular number lines, the x-axis and the y-axis. This plane is divided into 4 quadrants based on the signs of x and y. Let's look at 2 examples of relations defined by equations. First, consider the equation y equals x plus 3. This is a linear relation. For every x value, there is a corresponding y value. For example, if x is 0, y is 3. If x is 1, y is 4. The graph is a straight line. Next, consider the equation x equals y squared. This is a quadratic relation. If we choose an x value, say x equals 4, we find that y can be either 2 or -2. The graph is a parabola that opens to the right. It's important to remember that not all relations can be defined by a simple equation. Here are 2 examples. First, we can have a relation that is an infinite set of points, like all the points in the first quadrant, where x is greater than 0 and y is greater than 0. This is a region, not a line or curve. Second, a relation can be a finite set of discrete points, like these 13 points plotted on the plane. There's no equation that connects them in a continuous way. Now, we're ready to introduce a very special type of relation, a function. A function, sometimes called a mapping, is a relation where no two different ordered pairs have the same x-coordinate. In simpler terms, for every input, there is exactly one output. This is a crucial distinction. Every function is a relation, but not every relation is a function. A function is a special, well-behaved relation. So how can we tell if a relation is a function? We have 2 main tests. The first is the algebraic test. If you have an equation, substitute any value for x. If you always get 1 and only one value for y, then it's a function. Let's apply this. For y equals 3x minus 1, if x is 2, y is 5. There's no other possibility, so it's a function. But for x equals y squared, if x is 4, y can be 2 or -2. Since there are 2 outputs for one input, it's not a function. The second test is the geometric test, or vertical line test. If you draw all possible vertical lines on the graph of a relation, it's a function if each line cuts the graph no more than once. If any vertical line cuts the graph more than once, it's not a function. Let's use the vertical line test on some graphs. Consider this graph. If we draw any vertical line, it will only ever cross the curve once. Therefore, this is a function. Now look at this graph. Again, any vertical line we draw will intersect the curve at most once. This is also a function. Finally, let's test this graph. If we draw a vertical line, we can see it intersects the curve at 2 different points. Because we found at least one vertical line that crosses the graph more than once, this relation is not a function. Let's practice with a few more examples from your notes. First, we have a set of ordered pairs. To check if it's a function, we look at the x-coordinates. They are 1, 2, 3, and 4. Since all the x-coordinates are unique, this is a function. Next, consider this set. The x-coordinates are 2, 2, 2, and 2. The input 2 is mapped to 4 different outputs, -1, 0, 3, and 11. This violates the definition of a function, so it is not a function. Let's try one more. Here, the x-coordinates are 0, 1, 3, and 5. All are unique. The y-coordinates are all 0, but that's perfectly fine. A function can have the same output for different inputs, it just can't have different outputs for the same input. So this is a function. Now that we can identify functions, let's learn how to write them using function notation. A helpful way to think about a function is as a machine. You put an input, x, into the machine, and it performs a set of operations to produce a single output. For example, this machine doubles the input and then adds 3. If we put in 4, the output is 2 times 4 plus 3, which equals 11. In mathematics, we use a special notation to represent this process. We can write f is the function that converts x into 2x plus 3. A more compact way is to write f colon x maps to 2x plus 3. This is read as f of x is mapped to 2x plus 3. There are 2 other equivalent forms that are very common. We can write f of x equals 2x plus 3 or y equals 2x plus 3. All 3 notations mean the same thing. The expression f of x is called the function value or the image of x. It represents the output of the function for a given input x. Let's see how to use this notation to evaluate functions. Suppose we have the function f of x equals 2x squared minus 3x. To find f of 5, we replace every x in the expression with 5. This gives us 2 times 5 squared minus 3 times 5, which simplifies to 35. Similarly, to find f of negative 4, we replace x with negative 4. Remember to use parentheses to avoid sign errors. This gives us 2 times negative 4 squared minus 3 times negative 4, which simplifies to 44. We can also substitute expressions, not just numbers. Let's find f of negative x. For the function f of x equals 5 minus x squared. We replace every x with negative x. This gives us 5 minus negative x squared, which simplifies to 5 plus x minus x squared. Now let's find f of x plus 2. We replace every x with the expression x plus 2. This gives us 5 minus the quantity x plus 2 minus the quantity x plus 2 squared. Expanding and simplifying this expression gives us negative x squared minus 5x minus 1. Let's work through a few more examples to solidify our understanding of function notation. Consider the function g of x equals the quantity 2x plus 3 divided by the quantity x minus 4. First, let's evaluate g of 2. We substitute 2 for x, which gives us 7 over negative 2, or negative 3.5. Next, let's find a value of x for which g of x does not exist. A fraction is undefined when its denominator is 0. So we set x minus 4 equal to 0 and solve for x. This gives us x equals 4. Therefore, g of 4 is undefined. Now, let's find g of x plus 2 in simplest form. We replace every x with x plus 2. This gives us 2 times the quantity x plus 2 plus 3 all over the quantity x plus 2 minus 4. Expanding the numerator gives 2x plus 7. Simplifying the denominator gives x minus 2, so g of x plus 2 is 2x plus 7 over x minus 2. Finally, Let's find x if g of x equals negative 3. We set the expression for g of x equal to negative 3. Multiplying both sides by x minus 4 gives 2x plus 3 equals negative 3x plus 12. Solving for x, we find that x equals 9 over 5, or 1.8. Let's look at a real-world application. The value of a photocopier T years after purchase is given by the function v of t equals 9,650 minus 860t. First, let's find v of 4. Substituting 4 for t gives 6,210. This means that 4 years after purchase, the photocopier is worth 6,210 euros. Next, let's find t when v of t equals 5,780. We set the function equal to 5,780 and solve for t. This gives t equals 4.5. This means it takes 4.5 years for the photocopier's value to drop to 5,780 euros. Finally, let's find the original purchase price. This is the value when t equals 0. Substituting 0 for t gives 9,650. So the original purchase price was 9,650 euros. We've seen that the domain is the set of all possible inputs, and the range is the set of all possible outputs. Now let's look at how to describe these sets using different notations. We can use set notation, interval notation, or a number line graph. Let's review these. For numbers between a and b, including a and b, we write x is greater than or equal to a and less than or equal to b. In interval notation, this is a closed interval from a to b, written with square brackets. On a number line, we use solid circles at a and b and shade the segment between them. For numbers outside a and b, we write x is less than a, or x is greater than b. In interval notation, this is the union of two open intervals, from negative infinity to a, and from b to positive infinity. On a number line, we use open circles at a and b and shade the lines to the left of a and to the right of b. Let's find the domain and range of some functions by looking at their graphs. Consider this graph. The arrows indicate it extends infinitely to the left and right, so the domain is all real numbers. The lowest point on the graph is at y equals negative 3, and it extends infinitely upwards. So the range is all real numbers greater than or equal to negative 3. Next, let's look at this graph. The domain is the set of all x values for which the graph exists. The graph starts at x equals negative 1 and ends at x equals 5. The open circle at negative 1 means it's not included, and the closed circle at 5 means it is. So the domain is the interval from negative 1 to 5, with 5 included. The range is the set of all y values. The lowest y value is 1, and the highest is 3. So the range is the interval from 1 to 3, with 3 included. Finally, let's analyze this graph. The graph has a vertical asymptote at x equals 2, meaning the function is not defined there, so the domain is all real numbers except 2. The graph also has a horizontal asymptote at y equals negative 1, meaning the function never reaches this value, so the range is all real numbers except negative 1. Sometimes, the domain of a function is not explicitly stated. In these cases, we use the natural domain, which is the largest possible set of real numbers for which the function is defined. There are two main rules to remember when finding the natural domain. First, you cannot divide by 0. Second, you cannot take the square root of a negative number. Let's apply these rules to find the domain and range of some functions. Consider f of x equals the square root of x minus 5. For the square root to be a real number, the expression inside must be non-negative. So x minus 5 must be greater than or equal to 0, which means x must be greater than or equal to 5. This is our domain. The square root of a non-negative number is always non-negative, so the range is all y values greater than or equal to 0. Next, consider f of x equals 1 over the quantity x minus 5. For this function to be defined, the denominator cannot be 0. So, x minus 5 cannot be 0, which means x cannot be 5. The domain is all real numbers except 5. The range is all real numbers except 0, because a fraction with a non-zero numerator can never be 0. Finally, let's look at f of x equals 1 over the square root of x minus 5. Here, we have both rules at play. The denominator cannot be 0, so x minus 5 cannot be 0. And the expression inside the square root must be non-negative, so x minus 5 must be greater than or equal to 0. Combining these, we get x minus 5 must be strictly greater than 0, which means x must be greater than 5. This is our domain. The range is all positive real numbers, because the square root is non-negative and the fraction is non-zero. Let's try a more complex example. Find the domain of f of x equals negative 7 over the square root of 3 minus 2x. The denominator cannot be 0, and the expression inside the square root must be non-negative. So 3 minus 2x must be strictly greater than 0. Solving this inequality, we get 3 is greater than 2x, or x is less than 1.5. This is our domain. Let's explore a fascinating application of functions. Fluid filling. Imagine filling a container with water at a constant rate. We can graph the depth of the water over time. If the container is a cylinder, the volume of water is directly proportional to the depth. Since we're adding water at a constant rate, the depth increases linearly with time. The graph is a straight line. Now, what if the container is a cone, wider at the top? As we add water, the depth increases. But because the container gets wider, the same amount of water causes a smaller increase in depth. This means the rate of change of depth is decreasing. The graph is a curve that starts steep and flattens out. Let's predict the depth-time graphs for some other shapes. Consider this container. It has a narrow cylindrical base and a wider cylindrical top. The first part of the graph will be a straight line with a steep slope, representing the rapid increase in depth in the narrow base. Then, when the water reaches the wider top, the slope will suddenly become less steep, resulting in a graph with two linear segments. Now, what about this container, which is wider in the middle and narrower at the top and bottom? The graph will start with a steep slope, then the slope will decrease as the container widens, reaching a minimum slope at the widest point. After that, as the container narrows again, the slope will increase, becoming steeper. The graph will be a curve that is concave down and then concave up. This investigation shows a powerful connection between the physical shape of an object and the mathematical shape of its graph. The gradient of the depth-time graph tells us the rate at which the depth is changing. Finally, let's explore composite functions. This is when the output of one function becomes the input of another. Given two functions, f and g, the composite function f following g, written as f of g of x, means we apply function g first, and then apply function f to the result. Let's visualize this with our function machines. Suppose f of x equals x to the power of 4, and g of x equals 2x plus 3. To find f of g of x, we first put x into the g machine, which outputs 2x plus 3. Then, we take that output and put it into the f machine, which raises it to the power of 4. The final output is the quantity 2x plus 3, all to the power of 4. Algebraically, we write f of g of x equals f of the quantity 2x plus 3, which equals the quantity 2x plus 3, all to the power of 4. It's very important to note that the order matters. F of g of x is generally not the same as g of f of x. Let's find g of f of x. This time we put x into the f machine first, which outputs x to the power of 4. Then we put that into the g machine, which doubles it and adds 3. The final output is 2x to the power of 4 plus 3. Algebraically, g of f of x equals g of x to the power of 4, which equals 2x to the power of 4 plus 3. As you can see, the two results are different. Let's work through another example. Given f of x equals 2x plus 1 and g of x equals 3 minus 4x, let's find f of g of x. We substitute g of x into f, which gives us 2 times the quantity 3 minus 4x plus 1. Expanding and simplifying gives 7 minus 8x. Now let's find g of f of x. We substitute f of x into g, which gives us 3 minus 4, times the quantity 2x plus 1. Expanding and simplifying gives negative 8x minus 1. Again, the results are different. We can also evaluate composite functions for specific numerical inputs. Given f of x equals 6x minus 5 and g of x equals x squared plus x, let's find g of f of negative 1. The best way to do this is to work from the inside out. First, we find the value of the inner function. f of negative 1. Substituting negative 1 into f of x gives 6 times negative 1 minus 5, which is negative 11. Now we take this result, negative 11, and substitute it into the outer function, g. So we need to find g of negative 11. Substituting negative 11 into g of x gives negative 11 squared plus negative 11, which is 121 minus 11, or 110. So g of f of negative 1 is 110. Let's try another one. Let's find f of 0. This is a composite function of a function with itself. Again, we work from the inside out. First, find f of 0. Substituting 0 into f of x gives 6 times 0 minus 5, which is negative 5. Now, we substitute this result, negative 5, back into f. So we need to find f of negative 5. Substituting negative 5 into f of x gives 6 times negative 5 minus 5, which is negative 35. So f of 0 is negative 35. A final, very important point about composite functions is their domain. The domain of a composite function f of g of x depends on the domains of both f and g. Specifically, the input x must be in the domain of the inner function g, and the output g of x must be in the domain of the outer function f. For example, let f of x equal x squared and g of x equal the square root of x. The domain of g is x is greater than or equal to 0. The domain of f is all real numbers. The composite function f of g of x simplifies to x. However, its domain is not all real numbers. It's the domain of the inner function g, which is x is greater than or equal to 0. This is because the square root of x is only defined for non-negative numbers. Let's recap what we've learned today. We started by defining a relation as any set of ordered pairs. We then introduced the concept of a function as a special type of relation, where each input has exactly one output. We learned to test for functions using the algebraic test and the vertical line test. We explored function notation, f of x, and learned how to evaluate functions for both numerical and algebraic inputs. We also defined the domain as the set of all possible inputs, and the range as the set of all possible outputs. Finally, we studied composite functions, where one function's output becomes another's input, and we saw that the order of composition is crucial. You are now equipped to define and identify relations in functions, use function notation, and determine the domain and range of various functions. These skills are fundamental for your journey through higher-level mathematics. To help you practice and master these concepts, here are 5 questions with their answers. Take your time to work through them. Question 1. Which of these relations is a function? Question 2. If f of x equals 3x squared minus 2x plus 1, find f of negative 2. Question 3. Find the domain and range of the function f of x equals the square root of 4 minus x. Question 4. Given f of x equals 2x plus 5 and g of x equals x squared, find f of g of x and g of f of x. Question 5. Find the domain of the function h of x equals 1 over the quantity x squared minus 9. Pause the video here and try to solve them on your own. When you're ready, the answers will appear. Here are the answers. Check your work carefully. If you made any mistakes, go back and review the relevant section of the video. Thank you for watching.